So now that we know what a sequence is, and we know how to find and recognize the pattern within the sequence, we know how to find this general term an, we want to ask this question. We want to see what happens here to our sequence as n approaches infinity. So really, we can sort of go back to what we've learned in Cal 1. We're interested in knowing what's going to be the limit of our general term, okay, as n approaches infinity. So let's take a look back at this example that we saw before. If I want to do here the limit as n approaches infinity of 3n divided by 5 to the power of n, what do we get here? Well, unfortunately, right away we have that our numerator goes to infinity, and so does our denominator. So we have infinity divided by infinity, which is an indeterminate form. So we have here really one nice option, which is going to be to just use L'Hopital's rule, and we get limit as n approaches infinity. We differentiate 3n, which leaves us with 3. We differentiate 5 to the n, which you'll remember the derivative will be 5 to the n multiplied by ln of 5. So this is what we end up with for our limit, and now we can recognize that here our numerator is constant, it's just going to approach 3, but our denominator is not constant, it is still going to go to infinity, and so this whole thing altogether is going to approach a constant, in this case 3, divided by an ever-increasing denominator, and this whole thing is just going to go to 0. So for this one, we could say our sequence, okay, the terms in our sequence are going to be getting infinitely small as n approaches infinity, okay, because as n approaches infinity, we know that the terms in our sequence are going to approach 0. Now, we've seen in improper integrals the discussion of convergence and divergence. These two terms, convergent and divergent, are going to be again relevant when we talk about sequences and also when we talk about series. So now let's take a look at how they are defined in the context of sequences. So we know how to recognize our sequences, we know how to do our limit as n goes to infinity on a sequence, and really now talking about convergent and divergent, the definition is almost exactly the same as what we had for improper integrals. Okay, for an improper integral at the end, we would always be doing a limit, and if that limit existed, then the integral was convergent, and if it did not exist, then the integral diverged. This is exactly the same thing. If our limit exists, then the sequence is going to be convergent. However, if the limit does not exist, then our sequence right here is actually going to be divergent. Okay, so let's just take a look quickly again at the sequence that we just saw. Okay, we had 3n divided by 5 to the power of n from 1 to infinity. This is going to be convergent, and it is convergent because the limit as n approaches infinity of an, which in this case was 3n over 5 to the n, it was equal to 0. It existed. Okay, so this is very much what we're going to be looking at with sequences. We want to know when this limit exists and when this limit does not exist, so then we can know whether our sequence is going to be convergent or divergent. Okay, so let's actually just take a look at a couple examples. And really, this is going to be sort of a nice review from Cal 1 on indeterminate forms, doing limits, okay, and practicing with L'Hopital's rule. Okay, so here we're looking at whether our sequence converges or diverges, and if it converges, find the limit. So these questions actually, there's not too much to think about initially. If you want to know whether a sequence converges or diverges, for now, all that means to us is that we're going to take the limit as n goes to infinity on our general term. Okay, so for a here, we're going to be looking at what is the limit as n goes to infinity. N squared divided, or n squared here, multiplied by e to the negative n. And we check direct substitution, what happens as n goes to infinity. This part goes to infinity. However, this part goes to 0. So what we end up with here is going to be indeterminate form 0 multiplied by infinity. So we're going to have to use L'Hopital's rule. Now, the way that we're going to set up L'Hopital's rule is we want to convert this into either 0 over 0 or into infinity over infinity. So we want to choose one of these two functions to put into the denominator, and in this case we have the e to the negative n is essentially already in the denominator. So we have n squared over e to the n, and now we're going to have, instead of 0 times infinity, which indeterminate form do we have? We have infinity divided by infinity. Okay, so now we're perfectly set up to do L'Hopital's rule. Let's see what we end up with. So we have here limit as n approaches infinity. We have 2n in the numerator. And the denominator here, we have the derivative of e to the n will be e to the n. So now there's nothing really to clean up. There's nothing to simplify. We can check direct substitution, but unfortunately we still have infinity over infinity. So we can do L'Hopital's rule here one more time. And we end up in the numerator now with 2 divided by e to the n. And so now we have 2 in the numerator. Our denominator, though, goes to infinity. So we have a constant divided by an ever-increasing denominator that is going to approach 0. And so we get that our sequence, n squared e to the negative n from 1 to infinity, is convergent. Specifically, the terms converge to 0. So now let's take a look at our second example. Okay, so this is what we're looking at. Again, we want to know here what happens as n approaches infinity of 2 times sine n squared divided by n plus ln of n. So let's take a look at what happens as n approaches infinity. This term definitely goes to positive infinity, so does this term, and we end up with infinity plus infinity in the denominator. Nothing weird happening there. Together, our whole denominator just approaches positive infinity. Let's take a look at the numerator. We have sine of n squared. So really, this is our sine function, and the input is going to be increasing without bound. Now here, if you think about your sine function, remember your sine function is going to be oscillating forever. And so what happens to the y values of that curve as n increases? Well, really the y values themselves just keep bouncing sort of back and forth between here positive 1 and here negative 1. So they don't really approach any specific y value. The limit is not going to be positive 1. It's not going to be negative 1. Really, what we would say actually for this limit is that this limit just does not exist. Okay, now I'm not saying that the whole thing has a limit that doesn't exist. What I'm saying is that in the numerator, that limit does not exist. So here, I want you to think for a minute about what we can do here to actually fix this limit, to find the value of it. Think back to what you learned in Cal 1. What does this remind you of? So in Cal 1, you would have seen what's called the squeeze theorem. And that's very much what we can use here. Even though we're looking at a sequence rather than a function, we can still apply the squeeze theorem. And so that's exactly what we're going to do. We can start off here with our basic trig function. We have sine of n is always going to be bounded between 1 and minus 1. And so we're going to build from sine of n into this whole sequence. So we want to do that sort of in a couple ways. The first is that if sine of n is bounded in this way, then sine of n squared will actually have exactly the same range. Okay, it's still going to be bounded between minus 1 and 1. And then we could multiply by 2. So we get 2 times sine of n squared will be bounded between positive 2 and negative 2. And then we want to divide by n plus ln of n. And we have to do that again across the entire set of inequalities. So we have negative 2 divided by n plus ln of n. That's going to be our lower bound. Then we have our sequence that we built up to, divided by n plus ln of n. And over here, we're going to have positive 2 divided by n plus ln of n. Now, you will remember from the squeeze theorem that the next step is to take the limit here that we're looking at. Our limit is n going to infinity. So what we want to do is look at this term and look at this term as n approaches positive infinity. So here, this one is just going to approach negative 2 divided by an ever-increasing denominator. It's going to approach 0. This one, for exactly the same reason, is also going to approach 0. And so really what we have now is that our limit as n approaches infinity, 2 sine n squared divided by n plus ln of n, that's going to be bounded below by 0 and above by 0. And so here we end up getting that our limit as n approaches infinity, 2 times sine of n squared over n plus ln n is equal to 0 by the squeeze theorem. And so it is convergent. And so that is part B. Whoops. We have that it is convergent. Now let's take a look at part C. Okay, so I did realize here for part C that I had originally written these as x's. Of course, they should be n's. And so we want to know whether this sequence is going to converge or diverge. Let's take a look at the limit. So now limit as n approaches infinity, and we have e to the n plus 4 to the power of 1 over n. So let's try our direct substitution. Let's take a look at what happens. In this case, our base is going to get infinitely large, but our exponent is going to approach 0. So you need to recognize for this that this is actually going to be an indeterminate form, and it's indeterminate form infinity to the power of 0. It's one of the exponential terms. So what we're going to do now is take this exponential and we're going to turn it into the indeterminate form 0 multiplied by infinity. Okay, we do that because we know how to deal with 0 times infinity eventually using L'Hopital's rule. So how do we do that? Well, ultimately, what we're going to be doing is taking this exponent and bringing it down to the front. But to do that, we need to introduce a logarithm. So you have to remember from properties of logarithms and exponential functions that if you have the natural exponential and the natural logarithm composed with each other, they end up canceling each other out. In other words, e to the power of ln of y can be just rewritten as y. And I can go from this direction, from left to right, or if I want, I could rewrite y in terms of e to the ln of y. And that is very much what we're going to be doing here. Okay, we're going to essentially be taking this as our y term, and we're going to write it introducing an exponential and at the same time introducing here a logarithm. Okay, so what we get for our limit is going to be the limit as n approaches infinity. We introduce our exponential, and at the same time our logarithm. We end up with this all to the power of 1 over n. And again, this is perfect because now with the logarithm, we can bring that exponent down to in front of the logarithm. And so if we do that, what ends up happening with our indeterminate form? We have still our base of e. We have 1 over n ln of e to the n plus 4. And now let's take a look at what happens as n approaches infinity. This term here is going to just approach 0. But this term is still going to approach ln of an ever-increasing number, so it's actually going to be ever-increasing itself. It's going to go to infinity. So we have taken our indeterminate form, infinity to the power of 0, and we have turned it into an indeterminate form 0 times infinity. Okay, so now that we have 0 times infinity, we know we can rewrite it as either 0 over 0 or infinity over infinity, all that we're going to do is choose either this function or this one and rewrite it into the denominator. So in this case, I would say the choice is fairly straightforward because 1 over n is essentially already in the denominator. I could rewrite it as e to the ln of e to the n plus 4. Let's clean that up a bit. All divided by n. And now what happens as n approaches infinity? Well, this is going to go to infinity, and so does this one. So we have now infinity divided by infinity. We're set to use L'Hopital's rule. Okay, so fine, let's see what happens with that, and let's give ourselves maybe a bit more room here. Limit as n approaches infinity. We still have everything to the base of e, but now we're going to be doing the derivative of this logarithm right here. So we're going to need to do a bit of a chain rule. It'll be 1 divided by that inner function. So we have 1 over e to the n plus 4. And then we're going to have to multiply by here the derivative of that inner function, which will be e to the n. And this whole thing is going to still be divided by the derivative of n, which is just going to be 1. So really what we end up getting here is the limit as n approaches infinity. We have e to the power of e to the n over e to the n plus 4. Okay, and so now what happens here as n approaches infinity? Well, this part is still going to go to infinity, so does this part. So we do still have indeterminate form infinity divided by infinity. We can again do L'Hopital's rule. So let's do it one more time. Limit as n approaches infinity. We still have that original base of e and our exponent. If we do L'Hopital's, and let's actually just put in that h here to represent that we've done L'Hopital's, and let's put it in here as well. Okay, we have e to the n divided by e to the n. And now, looking at this exponent, even though it's still going to be technically infinity over infinity, we have that e to the n divided by e to the n will always just be equal to 1. So for this one, it's just going to approach e to the power of 1. Our entire limit is equal to e. And so that limit exists, and so our sequence which was e to the n plus 4 to the power of 1 over n, is going to be convergent. Okay, so that is the end of what we're going to be looking at for sequences. Okay, we have taken a look at defining them. We have seen and practiced a bit of pattern recognition, looking for that general term an. We also know what it means for a sequence to converge and what it means for a sequence to diverge. You are simply going to be looking at these limits, finding out whether that limit exists or not. Okay, so really make sure you go back, practice L'Hopital's rule. Okay, practice with indeterminate forms. Make sure you understand the basic idea behind a sequence, and next time what we're going to do is use sequences to take a look at what are called infinite series. Okay, and an infinite series is what we're going to spend sort of the next few weeks looking at together.